Hello everyone, it's me Gagan Kumar present over here to teach you. Let's move on to the video. So we will discuss electromagnetic induction. In this chapter already we have completed so many portions. Now today especially we'll see about mutual inductance. About mutual inductance. Okay. So this everything already we have completed. Mutual inductance and also if possible AC generator we'll see. So what is mutual inductance? Already last class I have discussed. If there are two coils, nearby coils. So one flux is affecting other. So if a current changes in one coil, then magnetic field will change. That flux changes will happen in another coil. And due to this, some induced EMF will produce. So here this phenomenon is called basically mutual inductance. So when there are two coils are there. So these two coils will study. So two solenoid, coaxial solenoid, or two coils, okay, or two circular loops, like that type of things we'll see here. And here already we have completed last class. What is inductance? What is self-inductance? And energy stored in inductor. Some questions, MCQ questions based on this we'll see. After that we'll come to mutual inductance. Okay. So already self-inductance. Already I have explained what is self-inductance. Now when there is one coil, and if current changes in this coil, then EMF is induced in the self coil. In the same coil, it will end. So that's why it is called self-inductance. Already given the idea, formula also given. Okay. So let's come to questions, MCQ question based on this inductance and all. After that, we'll come to mutual inductance. Okay. So this is our MCQ questions here, and this all questions will be given in the description box in PPT format. You can download it from the link. And here see, the first question is the self-inductance of a solenoid of length L and area of cross section A and having n turns is how much? So some options are given here. So you see, this is one coil is given here. This is a coil. Now here, what you need to find? Now length is given L. Length is L given. So usually we consider self-inductance is capital L, but in this case they have taken L. Length already taken L. So no need to worry. So now self-inductance I'll take as L prime. Now this. Okay. Or I can take L, but as length already taken capital L, so that's why I'm taking L prime. And here some options are given. Actually last class if you see, if a current is flowing I in this coil, already changing, this current is changing, then some flux changes will happen inside this. Due to that some self-inductance thing will come. So that is nothing but, this is what? Now mu naught n square A into L. Okay, this L is basically nothing but length of the solenoid. If area of cross section A and length is L, and here if n is the number of turns per unit length, then this is the formula already we have discussed. So now see, here this is small n square, but here nowhere is small n is there. So definitely the small n you have to change it to capital N by L square into AL. Now how much coming it is? Now mu naught n square by L square into AL. Now here if we'll cancel L and L square, it will be mu naught n square A by L. Here L prime is nothing but mu naught n square A by L. So now first option will be correct. So here answer is option A. The self-inductance of solenoid is mu naught small n square A into L. But now if small n will change it to capital N by L, then answer will come option A. Okay. So that one you try to understand. Okay. The question number 2. When the number of turns and length of the solenoid are doubled. So what they are telling here? Now here number of turns, that is capital N basically. Number of turns is capital N. The number of turns capital N and the length of the solenoid. Length means capital L or small l you tell. Small l also you can tell, no worries. Okay, small l. Doubled. Doubled means 2 times. It becomes 2 times. Now keeping the area of cross section same. Okay. Now the inductance what will happen to the inductance? So here are some options are given. Now listen, what is your inductance formula? L equal to mu naught n square A into L. So this is the formula we calculated last class for solenoid. And here this mu naught, if air is present inside solenoid, then mu naught will be there. And if you want capital N, number of turns is capital N, but small n is number of turns per unit length. Always remember that idea. Small n is capital N by L. So if you want capital N here, so substitute that and you will get mu naught n square A by L. Like this will be. L means small l I am taking. Small l is the length. Small l is the length of the inductance. Now listen. Now what they are telling here? Now if number of turns and length both are doubled, then what will happen? Now here let me write, this is L prime. The L prime, what is happening? Now mu naught, this number of turn is doubled, so it will become 2n. Now this is the original initial self inductance. Now this is the final self inductance if n doubled and area is same. Area same, no changes, and length is 2l. Now what is happening, you check here. Now it is 2 square 4, 4 by 2 2, so 2 into mu naught n square A by L. Now see here, so L prime is how much coming? Now L prime is nothing but 2 times, this is the length, this is the length. So whatever I am writing, this one is down is length only. So it is 2 times L. Capital L is self inductance, in this case I have taken, and small l is the length. Okay, and this is your new self inductance, L prime, new self inductance. Okay, so that is your coming 2 times original self inductance. So what is happening here? That is doubled. So answer is C. Answer is C. Got doubled. Yes or no? Yes. I hope you understand. So this is the formula actually. This small l is the length of the solenoid, capital L is the self inductance. Suppose they are given this one is capital L, then this one you can change something. L prime, L1 like that we can take. Okay. Now a 100 millihenry coil carries a current of 1 ampere. So L value is 100 millihenry, current is 1 ampere. So I is given 1 ampere and L is given 100 millihenry. Milli means 10 to the power minus 3. So millihenry is not SI unit. You have to convert to SI, means only Henry will be there. Then what is the energy stored? What is the energy stored in magnetic field? Energy stored means you have to find E or basically U. Okay, U or W you can tell. Okay, like this one. So this question mark I told. So what is the energy stored in inductor? Last class already I told. So energy stored in inductor. Energy stored in inductor is basically half Li square. Half Li square. So half into L value take 100 millihenry. So 100 into 10 to the power minus 3. And I is basically how much? I is basically 1 ampere. So it is 1 square. Now if you check this one, it is coming how much? Now 2 will cancel. 2 will cancel here. 100 as a 50. Now 50 into 10 to the power minus 3 joule. Or you can tell this one is, you can write 10 to the minus 3 1 by 1000. So 0.05 joule. 0.05 joule. Then calculate this. Okay. I hope you understand this one. So energy stored in inductor. So that's magnetic energy basically. You can UV also you can write. It is a magnetic energy. Okay. Sometimes UV also I'll write because it is a magnetic energy. So energy stored in inductor is nothing but what it is? Half Li square. Okay. So energy basically stored in the form of magnetic field. If the inductor is there, current is flowing, then energy stored in inductor is half Li square. Okay, I hope you understand. So try to solve yourself. So easy question only. Now the SI unit of inductance, the Henry, already you know this, and symbol is represented as capital H, can be written as what? Weber by ampere, volt into second by ampere, joule by ampere square, ohm into second, all of this. So see, everything is given here. So first let's understand what is self-inductance formula. Now self-inductance is total flux, magnetic flux, okay, by current. So magnetic flux is basically nothing but it is Weber, and current is nothing but it is ampere. So SI unit I can write Weber by ampere. So this is correct, or Weber into ampere inverse. So this is also correct. This is also can be written as like this. Now check second one. Volt is into second by ampere. So here volt into second by ampere given. So you can check this also. How you can check? Now inductance I have written like this. Sometimes you see L equal to E by di by dt. So like this also I have given already formula for self inductance. Now here if you see I can write this one as EMF into dt by di, or I can check here EMF means volt into second divided by current means ampere. Current means ampere. Now see here. Okay. So because dt and t same unit only. Change in time and time both will be same unit. In physics always a change in physical quantity and a physical quantity both will have same unit. So dt is a second, t also second. So I current is ampere, di also ampere unit. Okay. The unit will be same. Change in quantity unit. So volt into second also correct coming. Now check joule by ampere square. So already last class I told here. So you can check here how you can check. Now Weber, I told here you can check. Weber is nothing but it is Tesla into meter square by ampere. Tesla into meter square by ampere. Actually flux is magnetic field into area. Now this magnetic field is nothing but it is Newton by ampere into meter. Okay, into meter square by ampere. Now if you check here, meter and meter square will get cancelled. Meter and meter square will get cancelled. Down ampere into ampere will become ampere square, and up Newton into meter will become joule. Newton into meter will become joule. So joule by ampere square. Like this you can do. Otherwise, already you know energy stored in inductor, energy stored in magnetic energy stored in inductor is basically half Li square. Now self inductance if you want to find, you can write it is 2U by I square. Okay, U is basically energy is joule. So joule by ampere square. This also you can tell, that also you can say. So this is also correct. So all these three options are SI unit of the Henry. Okay. Ohm into second also not yes or no, that also you can check. That will be also unit SI unit of Henry. Okay, so Henry can be written into ohm into second also. How it is? Now see here. So here volt into second by ampere I wrote. So I can calculate from there. So volt is basically voltage. You know V equal to what? IR. I into resistance. So I can write ampere into ohm into second by ampere. Now ampere cancel. Okay, from here I am writing volt into second by ampere. Volt I converted what? Ampere into ohm. Okay, this is the ohm symbol I given. So that means what is happening? Ohm into second. Ohm into second is also SI unit of Henry. Inductance. SI unit of inductance. So that means what is happening in this question? This E will be correct. All of these SI units are correct for Henry. For Henry, all these SI units are correct. So you keep in mind everything correct here. Joule by meter square, ohm into second, volt into second by ampere, Weber by ampere also. Okay. I hope you understand. So answer will be what? Option E. Answer will be option E. And how all these things are coming, I have given some explanation here. Okay. Now the equivalent quantity of mass in electricity is what? The equivalent quantity of mass in electricity is basically inductance. Already I told you last class. I was giving example like this, half mv square and half Li square. So analogous you do. Okay, so here this mass and here inductance L. So these both are equivalent like, and speed and current and speed also. The equivalent quantity of speed in electricity is basically current. Okay, so that also you can understand. So how mass opposes motion? Okay, movement. Okay, translational motion. Similar way, inductance L. Inductance L will oppose what? Growth or decay of current. Okay, so current flow it will oppose. So that one you just keep in mind. Okay, so this is your equivalence questions. Okay. Okay, now next listen. When the current in a coil changes from 8 ampere to 2 ampere in 3 into 10 to the power minus 2 second. 8 ampere to what? 2 ampere in 3 into 10 to the minus 2 second. The EMF induced in the coil is 2 volt. The self inductance of coil in millihenry is how much? So what it is given actually? Now some changes given. Current in a coil changes means I changes is happening. What to what? 8 ampere to 2 ampere. 8 ampere to 2 ampere changes is happening. So how much changes you can tell? 6 ampere change. Okay, so basically decreasing, current is decreasing there. Okay. Now time is given here. How much time? Now this one 3 seconds. So let me write given data. After that we'll try to understand. So what is given? That change in current Ti equal to 6 ampere. Okay, it is decreasing. As there is no need to calculate any EMF and directions and all here, so no need to worry for decreasing, but write Di, change in current is Di, and in that time dt is how much given? The time interval is 3 into 10 to the power minus 2 second. Okay, now the EMF induced, the E, so they are asking what is the EMF induced. Already we know what formula we know. Now we know that EMF equal to L di by dt. L di by dt. Okay. So this one we know. Now if you want to find L, then what will do? EMF magnitude, then di by dt. So everything is given here. Now you substitute yourself and calculate. Everything given in SI unit. So you substitute and calculate. Okay. So sorry, EMF induced in the coil is 2 volt. It is given here. EMF induced is 2 volt. 2 volt. Okay. So you have to find L. You have to find L. So EMF is given 2 volt. Now you have to find what? L. So try to calculate yourself. Induced EMF is already given, but they are asking L. Induced EMF is given, they are asking L. Now see, induced EMF is 2 volt. So put here 2 here divided by Ti is nothing but it is 6 ampere. 6 divided by 3 into 10 to the power minus 2 second. Okay. So now this will go up. So 2 into 3 into 10 to the power minus 2 divided by 6. Now 6 will get cancelled. It will be 10 to the power minus 2 Henry. Okay. So in SI unit I am calculating. So it is coming how much? 10 to the power minus 2 Henry. But here no options like that. They are telling answer you calculate in millihenry. So millihenry means to multiply 10 into 10 to the power minus 3 Henry, which is 10 millihenry. So 10 you multiply and 10 you divide, or you can write 10 to the power minus 2 as 10 into 10 to the power minus 3. That will become basically 10 millihenry. Okay, so answer you check here. Option D answer is coming 10 milli. Okay. So here Di is given, Dt is given, E also given. Now they are asking about this. They are asking about L. So what is L? So calculate it. Now see here the coefficient of self inductance. That is coefficient of self inductance and self inductance same thing only, L only. of a solenoid is 0.18 millihenry. So this is already given L here. If a rod of soft iron of relative permeability 900, so relative permeability means mu r. So mu r is given. Then the coefficient of self-inductance will become nearly how much? Okay. So what they are telling? Now one self-inductance of solenoid is given. If a mu r is inserted in the solenoid, so a solenoid is like this. It has certain L value. And L value is 0.18 millihenry. Okay. Now inside this what I am doing now? I am putting some type of material, suppose some type of material I am keeping. This material permeability is mu r. If that one I am keeping, then what is my L prime? What is my L prime? Okay. So last of already a formula we discussed. What do we discuss? Now L equal to, if air is present, it is mu naught n square Al like this. If any material is present, then it will be what? Mu r mu naught n square Al. Already we have discussed. Now from here I can write L prime is nothing but it is mu r into L, because this will be nothing but L. Okay. So try to understand. If air is present, L is this. If any medium is present inside solenoid, then inductance formula will be this one. That one I am given as L prime, or you can write also L medium. Sometimes Lm you can write L medium like that. I am giving as L prime. Okay. So that time what? This mu naught will become mu. And mu, you know what? Mu is nothing but mu r into mu naught. This mu r is called what? Relative permeability. Remember, relative permeability. So what is this L prime is coming? Now it is coming basically what? Mu r into L. So just multiply. So mu r is 900 into how much it is given? 0.18 millihenry. So multiply and you check which option is matching. Okay. So option A is given 2.4 and option B is given 5.4. Option A is given and option B is given 162. So 900 into 0.18 you do. You check, answer is coming 162, and here answer is given also option B. Option B. Okay. So L prime equal to nothing but mu r into L. Mu r into L. So relative permeability into self inductance value in air. So when inside solenoid air is there, this is the formula. When solenoid some material is present, this is the formula. Okay. So you can calculate, or you can pause the video also, you can do. Okay, otherwise this PPT will be available in the description box. Okay, I hope you understand. So let me go for next question. If you want this to write, you just pause the video and write. Okay. Now the current passing through a chalk coil of 5 Henry is decreasing at a rate of 2 ampere per second. What is decreasing? 2 ampere per second. The EMF developing across the coil is what? So what they are telling here? Now current is decreasing di by dt. Okay, this is given actually. Given that di by dt is how much? Now 2 ampere per second. The decreasing means I'll give a minus sign. I can write decreasing, but here minus sign I'll give. Why a minus sign giving? Because here some minus plus answers are there. And chalk coil, that means that is inductor only. Chalk coil L equal to what? 5 Henry. This is also given here. Sir, L equal to 5 Henry. Okay. di by dt this much and L is this one. EMF is developing. How much EMF? You know EMF is nothing but that is L. So the magnitude I will not find magnitude here because minus also given. So E equal to minus L di by dt. Minus L di by dt. This is the exact formula. So when I am taking magnitude, that time it is becoming what? When magnitude I will take, it will become L di by dt. But in the question also they did not ask the magnitude of EMF. They directly asked what is the EMF. So this is the EMF. Okay, or usually you write like this EMF. Okay, write like this. So minus L di by dt. Now put here minus L is given what? 5 is given. So 5 you put here. L is 5. And di by dt, as it is decreasing. So this one you understand. Current is decreasing means definitely what will happen? Now this rate, whatever given, it is negative you have to take. Increasing means positive. Decreasing means negative. So minus 2. Now multiply, it will come plus 10 volt. Answer is coming how much? Okay, remember EMF SI unit is volt, so plus 10 volt. So option is given A. So this hints remember. So when di by dt they are telling decreasing, they are telling you have to take minus. Current is minus. Current rate of change of current is minus. Okay. Now check here. So here they are telling the network is given. In this network, a part of complete circuit is given. So here it is A, here it is B. And they're asking what is VA minus VB. So question is what asking? What is VA minus VB? So this is the question. And here what is given here? Here given a steady current 5 ampere is flowing. At this instant some current is there 5 ampere. So let me take this I here. Let me take I here. I equal to 5 ampere and L is given, this R value, this R resistor, this is a battery is there, L equal to 5 millihenry, 5 millihenry. Okay. Now they are asking what is the and current rate also given. So here di by dt. So current is decreasing at the rate of 10 to the power 3 ampere per second. So here what is happening? Now di by dt in this circuit, when current is going, the change in current is there, di by dt is there, 10 to the power 3 ampere by second. So now what to do here? Now listen. So what we'll do? Now we'll calculate KVL will apply. Already last class one example I given like this. So KVL will apply, will start from point A and will go in this path. We'll start from A, will go to B. And so first I'm starting from A, applying KVL. So I'll write VA. Then here current is going I, resistance is R. So VA minus I into R. I'll do here I into R, or directly let me write this one as how much? Now 5. So why minus 5? Because current into resistor will give you potential. So what is the potential drop here? 5 into 1 is 5. And when I'm going from here, I'm going from higher potential to lower potential. So there is drop in voltage. That's why one negative sign is coming. There is a drop in voltage. Now here it is 15 volt is their battery, and you are going from lower potential to higher potential. This is your path actually. Try to understand. This is your path. In this path you are moving, and here one battery is coming, one cell is coming. This cell negative terminal, this is positive terminal. When you are going like this, you are going from lower potential to higher potential. So there will be increase in potential. So that's your right here, plus 15 volt. Okay, so volt you don't need to write, you write just plus 15. So when you are going from higher potential to lower potential, that time decrease in potential. So that minus by 5 you are writing. And when you are going from lower to higher potential, that time what? Increase in potential. So that's why it is plus 15. Now here what will happen now? Now this will act like a battery or cell. So how the cell will be? If current is decreasing, whatever current is flowing here will be decreasing, it will try to increase the current, so it will act like a battery like this. So right side will be positive and left side will be negative. So that inductor will act like a cell. Already last class I discussed. So here what will happen? Now here this inductor potential will be how much? Now calculation to L di by dt. So L is given already 5 millihenry, that is 5 into 10 to the power minus 3. So if you will multiply this one, you will get here 5 volt. Okay. So di by dt and L if you multiply, you will get 5 volt. Try to understand. Inductor is there, current is decreasing. If the current is decreasing, then inductor will act like a cell and it will try to oppose the current. Which way? Now if current is decreasing, it will try to increase the current. Okay, in the circuit, if current is decreasing, due to decrease, the flux changes is happening in the inductor. Inductor is acting like a cell. Inductor is acting like a cell, and now what will inductor will do? Inductor will try to increase the current. If current is decreasing at the rate of this one is decreasing, negative actually I have decreasing. So what will happen? The current will inductor will try to increase the current. If di by dt is increasing, then inductor will try to decrease. So that this means this terminal will be opposite way. The terminal, both terminal positive and negative terminal will be opposite way. Okay. But here see, when EMF I am calculating, I have taken here all positive things because a magnitude I calculated. Because battery sign already given. So in applying KVL, that battery sign will help here, and magnitude I taken. Now see, I am again going from this battery lower terminal to higher terminal. So there is increase in potential. So it will be plus 5 volt, and I reached B. I reached the B point. So it will be VB. So now what you do? Now minus 5 plus 5 we will cancel. Now VA. Okay. VA minus VB is coming basically how much? Minus 15 volt. Okay. You can check this. So here minus all nothing is given in minus, so you can write in plus answer. Okay, write in plus, but actually VB minus VA will become plus 15. If you VA minus VB you are telling it can become minus 15. Okay. So anyhow potential difference is 15 volt is there. So check that current direction and accordingly you do. Sensor is coming C. Now come to next. A solenoid of length L meter has self inductance L Henry. Self inductance L Henry, and the number of turns are doubled, then its self inductance will become what? Already you know self inductance is directly proportional to number of turns square, n square. If number of turns is doubled, then what will happen? Now this self inductance definitely what will happen? It will become 4 times self. Okay, so that idea just keep in mind. So it will be 4 times. So answer will be C. Answer will be option C. Okay. So I hope you understand. So L is directly proportional to n square. If n is double, then it will happen what? N square will happen. Okay. Now let's move to the mutual inductance. We discussed MCQ based on the yesterday class. Now last class that self inductance. Now come to mutual inductance. Now understand what is mutual inductance. Already I discussed when there are 2 coils needed for mutual inductance, and if current is changing in one coil, okay, so due to that one flux changes is happening in other coil, so that they are telling an electric current can be induced in a coil by flux change produced by another coil in its nearby coil. Okay, this phenomenon is called mutual induction. And what is mutual inductance? The same thing, that this is the property actually. Remember, mutual inductance is the property of the coil which affects or change the current and voltage in a secondary coil. It's called basically mutual inductance. If definition type of torques are coming, then you can write this: what is mutual inductance and what is mutual induction. So 2 coils are there. In this coil nearby, they both should be nearby. Okay. So if current is changing in one coil, then magnetic field is changing. Due to that, some flux changes is happening in another coil. In that another coil, a induced current is producing or induced EMF is producing. So this is what the thing. Okay. Now for simple explanation, just consider 2 coils C1 and C2. So you can consider here one C1, coil C1 and coil C2. Okay. Now here magnetic flux. So magnetic flux is basically what? The magnetic flux is directly proportional to current I, where I is the strength of current in coil 2. So remember, magnetic flux in coil 1. So this is basically 1, this is basically 2, current in 2. So whatever current is flowing here, that current is affecting the flux of coil 1. So that's why magnetic flux in coil 1, that 1 symbol I have given. That is coil 2. 2, that's why given I2. Now, magnetic flux in coil 1 is nothing but one proportionality constant. That proportionality constant to give 1, 2. So why I am giving 1, 2? Because that is nothing but what you can say. Now that is your mutual inductance of coil 1 with respect to coil 2. So like that one we can tell, or due to coil 2. So that's why M1 to 1 symbol you can give here. Or normally M you can say also. Okay, normally M you can say. Okay. Similarly, if you want to check about the flux 5B2, so 5B2 will be directly proportional to I1. Okay, because if it coil current is changing in coil 2, flux is changing in coil 1 due to that current. If the current is changing here, due to this current change, flux is changing here in coil 2. So 5B2 will be what? It will be directly proportional to I1. Okay, so like that also you can do. Now that EMF induced in the neighboring coil C1. So whatever EMF induced is what basically, and according to Faraday's law, E equal to minus d phi by dt. This is a flux 1 basically, flux 1. Now it is M12 into di2 by dt. di2 by dt. So that one you can understand. Or normally if I want to write only I can write here in this particular case. Later I can take two coils or coaxial solenoid, you can understand. Okay, but now also you can give the number. So EMF induced in the coil 1, it depends the rate of change of current in the coil 2. See, di2 by dt is coming. So I2 definitely will be coil current in the coil 2. So here it is I2. Okay, here it is I1. Are you understanding? So this is what the thing they are telling. So change in current in coil 2 is inducing an EMF in coil 1, C1 coil. Okay. So this property is called basically what? Property of coil is called basically mutual inductance, and this phenomenon is called mutual induction. Okay, mutual induction. So you can pause the video and you can write the notes. I'll go to the next thing. Just to understand how in other way we can explain this M mutual inductance. Okay. So here mutual inductance I can write basically M is minus E by EMF by di by dt, or when di by dt equal to 1, that time mutual inductance equal to E. Or you can write also M12, no worries. M12 it is di2 also you can write, or here also you can write di2, no worries. So that means mutual inductance in the coil 1, okay, with due to coil 2, that is basically what? Equal to EMF when the rate of change of current equal to 1. So that is what one definition you can write here. What is the definition? The mutual induction of two coils is equal to the EMF induced in one coil when rate of change of current through the other coil is unit. So this is the numerical way you can what? Understand the mutual induction. Suppose sometimes you want to define mutual inductance, you can write the definition, or numerical way also you can define like this. Okay. Now, so SI unit of mutual inductance is Henry. So this one already I discussed in the previous class. Self inductance, mutual inductance, both will be Henry. And for Henry, there are many things are there. Or you can write it is basically Joule by Ampere square. Or you can write Weber by Ampere. This also you can write. Okay. so many SI unit you can write. And what is the dimensional formula of mutual inductance? A dimension, it has a dimension of what I can write? Now M1 L2 T minus 2 A minus 2. So you can remember this one. You can remember this Joule by ampere square. Joule by ampere square is nothing but what? Now A2 will go up. So A to the power minus 2 M1 L2 T minus 2 A to the power minus. Okay. So this is also you can do here. So mutual inductance has a dimension of what? M1 L2 T minus 2 A minus 2. Okay. So now we'll do one question based on the mutual inductance. So this is the main idea about mutual inductance. This much things you remember. Okay, this much thing you remember about mutual inductance. And it is a scalar quantity, so no need vector integral sign. Okay. So now we'll see the next thing. Okay. Now here it is given a question. Derive the expression of the mutual inductance of two long coaxial solenoids, same length, wound one over another. So now see here how it is. Now one small solenoid is there. One small solenoid is there. Now above this solenoid, another solenoid is wound like this. Another solenoid is wound. So this is the thing is there, and this is the axis. This is the axis of the solenoid. Try to understand. So one small solenoid is there. Its radius is R1. So here it is given your radius is R1. Above that, another solenoid, not a contact, just very close. One solenoid is there, another solenoid is like this. So close contact, not that much contact is there. Okay, little gap is there here. So the first solenoid you are telling the red color, you can see this you are telling is basically S1. So this is your S1 is given here, S1. The radius is R1. And second solenoid is S2. Second solenoid yellow color, whatever given here, S2. Its radius is how much? R2. So here it is given its radius is R2. So this is your S2. Second one is S2. For S2, radius is R2. Okay. Now this is what you write. And next for this S1, you write number of turns is N1. And for S2, number of turns is N2. And current is flowing in S2 is I2. And here I can write for first coil, S1 coil, the number of turns is N1. Okay. So picture you do clearly, and the length is given here, length is L. So I fixed the length, both are having same length. Red color, yellow color, both are having same length. So this is the picture of two coaxial solenoid. Why coaxial solenoid? Because their axis is same. Both the axes are same. Okay, in the one axis, both the solenoids are there. Okay, so that's why what is happening here. Now the coaxial solenoid you are telling. Now consider two long coaxial solenoid. So that language you can write little. Length is L. Length is L. And radius. Radius of L you can write capital L also nor is. Inner solenoid S1 is R1 basically, and outer basically R2. And the number of turns for inner one is N1. S1 is inner one and S2 is outer one. Okay. So you can do the picture and you can write some language little here for derivation type question. Okay. Okay. Now let N1 and N2 be the turns. Already I told that one, so you can understand here. Now already I told I2 is the current. Let I2 be the current in the upper coil, that's S2 coil. And when this I2 is set up, that time a magnetic flux also, magnetic flux will set up in the flux, will set up on the coil 1. So when I2 is set up in the coil 1, sorry, coil 2, then flux will set up in the coil 1. Remember, due to this current, one flux will be there in the coil 1 because that magnetic field is coming here. When current is passing through the upper coil, that magnetic field will be in the inner coil. Okay, that magnetic field will affect there, and here some flux will be there in the inner coil. Okay, and this time inner coil there is no current I have given, but one current will induce now. Okay, due to mutual induction, current will induce. And here I can write now what is my N151. Now N151 is the total flux in my coil 1. So total flux leakage with my coil 1 is nothing but, or solenoid 1. My solenoid 1 is M12I2. This one already I told. So total number of the flux is directly proportional to I. This one already I discussed. So in coil 1, what is the total flux? Now it depends on the current in coil 2. And one proportionality constant that is called coefficient of mutual inductance. Okay, so that one you are writing. So now here what is M12? Mutual inductance of solenoid S1 with respect to solenoid S2 or due to solenoid S2. And also you know it is referred as coefficient of mutual induction, M12. M12 we wrote. Now what is the magnetic field due to a solenoid? In the first coil, suppose in this coil current is going, in the yellow color solenoid current is going I2, then what is the magnetic field along the axis? Now already in the previous classes you studied, magnetic field for a solenoid is basically mu naught Ni, N is the number of turns per unit length. Now here magnetic field due to S2 is nothing but number of turns in S2, number of turns per unit length, and current is flowing in S2. That's why I write B2 is nothing but, that is N2I2. Okay, because that field in the S1, in this region, in the axis region, the field is coming due to coil 2 or solenoid 2. So that's why that field name I'll give as B2. So what I gave, now B2 is nothing but it is mu naught N2I2. Sorry. Now next, after finding magnetic field, let me find the total flux. So when the total flux through the coil 1, N1, you know N equal to nothing but small n into L, because small n equal to capital N by L. So that is what we are substituting here. And we are taking here capital L is the length. Capital L is the length of the solenoid. Now this N1L and phi 1 is nothing but, phi 1 is what basically? Magnetic field into area of the smaller coil, smaller solenoid, inner solenoid, and magnetic field due to outer solenoid. So B to A1 coming. Okay. And this N1 phi 1 is nothing but it is M1 to I2. So that one I am substituting here. Already I have derived here. N1 phi 1 equal to M1 to I2. I'll give here. Now this N1L, this B2 is mu naught N2 I2, and A1 is pi R1 square. A1 is what? Pi R1 square. Now here you see I2 will get cancelled. Now whatever remaining, now M12 equal to mu naught N1 N2 pi R1 square L. Okay. So this is your mutual inductance. Mutual inductance of coil 1 or solenoid 1 with respect to solenoid 2. Okay, so this is your mutual inductance M12 you got. Okay, so remember here are two small n with N1 N2 is there, pi is there, R1 square there. Why pi R1 square coming? Because smaller solenoid area of cross section like a circle. So circle means pi R1 square will come. Okay, area will come pi R1 square. So here we calculated M12. Okay, similarly we can calculate also M21. So what is M21? The mutual inductance of solenoid 2 with respect to solenoid 1. That also we can calculate. But we don't need to do that. So up to this one we'll do. So for 2 coaxial solenoid, if question is coming, we'll do this one, and we can say that M21 if we'll calculate also it will be equal. Both will be same. That one we can say orally. Normally you can write that. Okay. So in the same way we can derive that, and we can solve. So what? Now M12 equal to M21. that is equal to capital M. So like this we can show, and where you can write here M21 is nothing but same thing, mutual inductance of solenoid 1 with respect to solenoid 2. S1, S2 I am writing. Okay. So that one you can remember. M12 and M21 both are equal and they are having magnitude same, which is mu naught N1 N2 pi R1 square. And here some little consideration is there also. So this consideration you can keep in mind, that is length of the solenoid is very much greater than R2. R2 is what? Radius of the solenoid 2, upper solenoid. Upper solenoid is R2 radius, inner solenoid is R1 radius. Okay. I hope you understand. Similar way, now we'll try to calculate mutual inductance of two coils. So you can check your NCERT example 6.9. Now we'll calculate that one. That will be very easy and you can remember the formula. So please note it down. Okay. Now here, example 6.9, try to understand two concentric circular coils. So two concentric circular coils are there. One is C1 and another is C2. One is C1, C2. Now this you can tell coil 1, its radius is R1. Another is coil 2, its radius is R2. R1, R2 radius. Okay, so this circular coil, they are telling here, see, circular coils. They are not solenoid and all. Not that type of picture, it is simple. Two coils, whatever you are watching like this. And R2 is large actually. R2 is large. Okay. Now here we need to find what? Now we need to find mutual inductance of this arrangement. What is the mutual inductance? Now first you consider some I2 current in the solenoid, the second solenoid. So you can take or coil 2 is your coil 1. Okay. So let I2 is what? I2 be the current in coil 2. I2 be the current in coil 2. So due to this current, there will be some magnetic field at the center. Okay. So now the magnetic field at center of the magnetic field and both the center same. So that telling here coaxially. So here axis will put, that axis will be same for both. The magnetic field at center, is how much? Now B2, which is nothing but mu naught I2 by 2R2. So from where this formula is coming? Mu naught I2 2R2. So you remember, okay, a circular coil. If current is flowing I at the center, magnetic field at the center is how much? That is mu naught I by 2 into, if radius is R for this coil, then mu naught I by 2R. So this one already we studied. Okay. So that's why the magnetic field at center is this one. Now the flux through, if the magnetic field is there, okay, magnetic field is there, the flux through the coil 2, sorry, coil 1, flux through the coil 1, inner coil is, that is phi 1, how much it will be? That will be magnetic field of coil 2 into area of coil 1. Okay, because flux equal to basically phi 1 is basically B into A. So as current is flowing in the second coil, then magnetic field is there. Due to the second coil, some magnetic field is there here. And if some area is there here, A1 area will be there. So that's why B2 into A1 is the total flux for the coil 1. Okay. Now if I write this one, so phi 1 equal to B2. So B2 formula already you know here. It is mu naught I2 by 2R2. And A1 is nothing but pi R1 square. Why A is pi R1 square? Because area of a circle is pi R square. If radius is R1, so it is pi R square. Okay. Now what you do? Now you write this one like this. phi 1 equal to mu naught pi r1 square divided by 2r2 into I2. Now mu naught pi r1 square by 2r2, this is a constant now. Okay. So, and this is what term? Now you know flux equal to some constant into what? Current. So that constant is nothing but it's termed as here mutual inductance. So now we'll give here what it is, the mutual inductance. Okay, you can tell sir here N and L you did not multiply and all, because here they are telling only one coil, coil 1, coil 2, that's it. So no need to N and L, no need to consider. Okay, so like this. So that means I hope you understand here. So what is the flux? Flux you got. After flux, you will compare this equation. You compare this equation. You can write equation 1. Compare this equation 1 with the equation 2. That equation 2 I will write now. Okay. So first to complete this, you can pause video and you can complete. I will go to the next thing. So here, so let me write here otherwise. Let me write. Suppose phi 1 can be written as like this, M12 I2. So that means here comparing equation 1 and 2, comparing equation 1 and 2, what will get? M12 equal to mu naught pi r1 square by 2r. Okay, so this will be your mutual inductance. Mutual inductance of coil 1 with respect to coil 2 or due to coil. And remember, M12 will be nothing but it is equal to what? It is equal to M21. Okay, that also remember. M12 is nothing but what? Now M12 will be equal to M21. The similar way you can prove it. Okay, but remember here while solving this one, some consideration is also there. The magnetic field due to this coil 2, whatever at the center, that is actually uniform throughout this area of coil 1. That consideration we have taken. Okay, because if it is not exactly, this coil is not exactly at the center, little some radius is there. Okay, so that means here what now, if here I am taking magnetic field, what about here, what about here? Okay, so then variation of magnetic field will happen. So what I'll tell that magnetic field whatever B2, it is throughout this area. Okay, so that type of things you can understand. Okay, so that consideration we have taken. You can remember this. So this one sometimes direct questions can ask also. So star mark point, remember this one directly can ask if R1 R2 is there, then what is the mutual inductance. So in this way you can calculate mutual inductance. So direct formula remember, along with the derivation also you check. Okay, so you pause it and try to write. If I have not completed, let me go to the next class. So next topic. So what is the next topic? The coefficient of coupling. So what is coefficient of coupling? It can be defined as the fraction of magnetic flux produced by the current in one coil that links with the other. So basically symbol is denoted by K, and this K is what basically they are telling. Now if two coils are there, okay, or two solenoid coils, whatever inductors are there, okay. Now what is happening now here? Some flux, some magnetic field change, current is changing here, some magnetic field is changing. Due to that magnetic field change, some flux change is happening here. Okay. So here what is now some affection, some interaction is there between the two coils. If two coils are nearby, they are not magnetically isolated. They are nearby like this. So if current is coming here, some magnetic field is coming, that magnetic field is affecting here, that flux is affecting here. Okay. So there is some interaction. To understand the interaction between the two inductor or two coils or two solenoids, okay. So what we need? Now we need this quantity, coefficient of coupling. Okay. So this will define the things. Okay. Now suppose two inductors are there, L1, L2, and here that coefficient of coupling will how much? Now mutual inductance by L1, L2 root. Okay. It will be like this. Formula will be there. Now we'll derive this formula also little. We'll see proof how it is coming. Okay. So now M is basically mutual inductance and L1, L2 is self inductance. Okay, self inductance. Okay. Now suppose you want to prove this, how it is coming. Prove this. Now what we'll do here? So first thing you understood. So K is basically is a factor or constant, basically coefficient of coupling constant you can tell, which basically tells what? Now how two coils are interacting. How two coils are interacting. Okay. Now if L1 is there here one coil, L2 is there one coil. Now let current is flowing I1 here, current is flowing I1, and here current is flowing I2. And the number of turns is N1, here number of turns is N2. Now if you write what is the self inductance. So for both the things you will write what is, from this picture you can start self inductances. Okay. Directly write here. Okay, right here for coil 1, or solenoid 1. Okay, so what is self inductance? The self inductance will be L1, that is number of turns N1, whatever flux is changing phi 1, suppose here phi 1 flux, here flux changes is phi 2, so phi 1 by I1. Okay. And if you want to find what is the mutual inductance, what is your mutual inductance? The mutual inductance will be M12, which is equal to M21 also, we know, M12. So that will be nothing but K phi 1 into N2 divided by I1. Okay. So remember this one. So why this K term coming? Now due to both together are there, there's some linkage is there, some interaction is there. That interaction factor I took K. So that's why I told total flux in the L1 is nothing but that is K into phi 1. Similarly, if I'll calculate for coil 2, let me calculate for coil 2. Okay, coil 2 means second coil, what I have written here. I given L1, L2, or it write here C1 coil, C2 coil. Okay. Now coil 2, so you can write self inductance, that is your L2, which is N2 phi 2 by I2. And if you write what is the mutual inductance, okay, that is your basically M21, that is nothing but K into similar way phi 2 into N1 divided by I2 divided by I2 divided by I2. Okay. So K, here it is K phi 2 N1 by I2. Now what we will do? Now you know M12 equal to M21. Already you know this. That is equal to M. Now this mutual inductance will take and will try to find this expression, this coefficient of coupling expression. Okay. So now what I'll do here? Here I'll multiply. So but this basically I want to find the relation. This is what you can tell also. This you can tell relation between M, K and L1, L2. Okay, M and K, L1 and L2. Okay, that also you can tell. M, L1, L2 and K. So this is the relation you are finding. Okay, relation you are finding. Now, see, this relation I want to find means I can just tell M12 into M21. So I'll just write M12 and M21. So here I find M21, M12 and here M21. Now multiply that. Well, multiply that. Okay, or you can write equation 1 and equation 2. So multiplying equation 1 and 2. This is the equation 1, this is the equation 2. Okay. Now okay, so we are discussing about coefficient of coupling. So what I told about this actually, now when two coils, when two coils, nearby coils are there, when two nearby coils are there, okay, so when two nearby coils are there, coil 1, coil 2, having self inductance L1, self inductance L2, number of turns N1, number of turns N2, current I1, current I2, okay. So like these terms are there. Here flux phi 1, here flux phi 2, like that it terms are there. Okay. Then what will happen here? Now there will be some interaction. The magnetic field of this will be here. It will affect here. The magnetic field of this one will affect this one. The flux will be get affected. Both the fluxes will get affected. Some what will happen? Some interaction will be there between the two coils. So how to measure that interaction? Okay. So we need one quantity. That quantity is coefficient of coupling. Okay, so one constant quantity we need. Now what they are telling basically according to definition wise. Now definition wise is a fraction of the magnetic flux produced by the current in one coil that links the other coil. Okay, so it is a fraction of magnetic flux produced by the current in one coil that links to the other coil. Like that one they are explaining. But here what I'll do in terms of L1, L2 and in terms of mutual inductance we'll see what is this K. So this K also symbol is given K, coefficient of coupling constant, is basically what it is. Now, M divided by root under L1, L2. So this is the formula I can remember. Okay. So this is normal formula. And this K value also varies from 0 to 1. That one I'll say. K0 means these two coils will never affect each other. K equal to 1 means they will perfectly affect, they perfectly coupled. So this is a coupling actually. Okay, coupling of the coil. Coupling means you understand two coils are together you are keeping, three coils are together you are keeping, like that. A simple case, two cases we are taking here. Okay. So now our work is how this expression is coming. That one will try to understand. And here what is this? Now here this M is nothing but mutual inductance. Okay. Mutual inductance of the coils. Mutual inductance of two coils. Okay. And L1, L2, L1 is self inductance of coil 1, self inductance of coil 1 or solenoid 1, whatever. So let me tell coil. Self inductance of inductor also you can tell. Inductance of coil 2. Okay. So now what will happen? Now this K if I want to calculate, so I have to consider little some terms here. After that I can find this K. So for that one what I'll do first, let me write for coil 1, for coil 1, so let me check what is the self inductance. Self inductance. Now that is your L1. What will be L1? Now in the self coil, in the same coil, whatever self inductance you are telling, that depends on the N1, I1 and phi 1. So no need to go for any other term, just N1 phi 1 by I1, right? Now if you want to find for mutual inductance, here little things changes we'll see. So what is that one? Now M12, because I am finding mutual inductance of coil 1 with respect to coil 2. M12 meaning mutual inductance of coil 1 with respect to coil 2, that is your K into phi 2. This is the total flux. K into phi 1 into N2 divided by I1. So why I did like this? Because here when both are together, I told some effect will happen. This flux will affect there, that field will affect there, like that type of things happening. So whatever total flux, I'm taking what? K phi 2. K is a measure of constant, how much affection is happening, like interaction is happening. That's why K phi 2 I took total flux. Now similarly, if I'll find for coil 2, what is the self inductance? Self inductance for coil 2, all will be each term only 2 terms only, that is that L2, suppose you are telling here, okay. L2, now that is your N2 phi 2 by I2. If I want to tell what is mutual inductance, what is mutual inductance? Mutual inductance, it will be M21, which is nothing but K phi 2 N1 divided by what? I2 divided by. This is your equation 2 you give, and this is your equation 1 you give. Equation 1 and 2. And what we know? Now we know that M12 equal to M21. Already we know this. That is equal to M. Okay. M1 to M21 both are same. So both the two situations already we have calculated before. Now here what I do, let multiply equation 1 and 2. Let's multiply equation 1 and 2. Let's see what is happening. We will multiply equation 1 and 2. It will be M12 into M21 will be nothing but, it is here, let's write K into phi 1 N2 by L by I1 into K phi 2 into N1 by I2. So this is the thing is coming. Just simply equation 1, 2 value, just substitute here, multiply. Now this is, you know, M1, M2 is nothing but it is M square. This is what basically M square, because this is also M, this is also M, both are same only. M square. Now what you do, here little arrangement you do. This one K and K will multiply, it will become K square. And here this N1 phi 1 I1 you arrange. N1 phi 1 by I1. Here you arrange N2 phi 2 by I2. N2 phi 2 by I2. Now N1 phi 1 I1 is nothing but it, you check this one, self inductance. And here is L1, and here self inductance L2 is nothing but what it is, N2 phi 2 by I2. Now you can write M square is nothing but it is K square into L1 into L2. So like this you can write now. So M is nothing but what? M square, K square into L1 into L2. Okay. So very simple, for coil 1, coil 2, right? Then after multiply equation 1 and 2, then you will get M square. Now this equation you can derive now. Okay, let me do in the next page. Let me do in the next page this one. Okay. So already equation 1, 2 I have, M square equal to K square, this much is already came, this much already we have. Now here what I'll write, so this one you no need to write, already we have, no need to write this one, already we have this, so remove this one, no need to write. So you start from where? Now M square. So M square equal to how much? It is your K square L1 L2. Why L1 L2? Because already I have told you here, Self inductance is nothing but this N1 phi1 by I1. Already written also here. Okay, because flux by current already last class also I told that one. Now if I write M here, then root you have to take, then it will be K L1 L2 root. Now if you want to find K here, it will be M divided by L1 L2 root. So whatever you got here, this one, this is your coefficient of coupling. Coefficient of coupling. Okay. Or you can tell basically this is what? This is basically relation. You can tell it is also relation between coefficient of coupling and mutual inductance and self inductance between M, L1, L2 and K. So that relation also you can calculate. Okay, so your root is there, one root is there, because this will come this side, so root will be there. So K equal to M divided by root under L1 into L2. Okay, root under L1. Now depending on K value, this M value you can decide. Depending on M value, you can decide K value. So we can do that also here. So let me write little some important thing. So Starmer point. So K value is between basically what? 0 to 1. And if K is 0, then coils are magnetically separated. Coils are magnetically separated. So the one flux does not affect other coil. So that is what basically K is 0. And if K 0 means that time what is happening? Now M value also 0. Remember K 0 means M 0. And if K equal to 1, this one is called basically perfect or ideal coupling. So that means one coil flux or one coil current changes or magnetic field changes will affect another coil. So that is your K equal to 1. If K equal to 1, then what is happening here? Now M will be root under L1 L2. Check. Okay. If K equal to 1, M will be what? Root under L1 L2. You can check it from this expression. Okay. So this is the idea. And for K equal to 0, so series in inductors in series already I discussed. So today little we will discuss about mutually coupled inductors in series also after this. So remember K value be changes, then how many things are happening, which you can understand here. Okay. And also remember if K equal to little greater than 0.5, then that is tightly coupled, you can tell. This is also perfectly tightly coupled. Okay. And if K is less than 0.5, then it is less tightly coupled, like that one we can tell. So this much idea you can remember. Okay. So this is whatever we did. This is the continuation of this one. Continuation of this. Okay. Coil 1, coil 2 you took and you calculated the things. Okay. Now next listen. I hope you understood this. Please note it down. So you can pause it and you note it down. I'll go to the next thing. So mutually coupled inductors in series. So what they telling? I have two inductors. They are in series. L1 inductor, L2 inductor. And here mutually coupled inductors in series. Then what will happen? Now your L equivalent will be L1 plus L2 plus 2 into mutual inductance. Okay. And if I am telling here K equal to 0, then M will become 0, then L equivalent will become L1 plus L2. If it is not tightly coupled, perfectly coupled, then what will happen? L equivalent will be L1 plus L2. That means if it is magnetically separated. Okay. If not like that, then this one you have to keep. So M is mutual inductance between the two coils. That is the series connection number 1. So two coils in series. Now suppose two coils in parallel. That one will see there. And here see, this is plus 2M I gave. And here what I am telling, Here current, whatever current is there, this current is the same direction. So you remember here. So current in the same direction. If current in the same direction in the two coils, then this is the formula is correct. So some derivation is there, no need derive. So just remember, in the two coil, if currents are going in the same direction, then this L equivalent inductance will be this one. Now, if current are flowing in opposite direction, series is there, but here for this one current is going this way, for this one current is going this way. It can happen also. So L1, L2 is there. Okay. Now here what is happening? Now here if you want to find L equivalent, it is L1 plus L2 minus 2M. Okay. So here two magnetic fields are supporting each other, but here two magnetic fields are opposing each other. So here currents are in the opposite direction. So here currents, what you write? Currents are in opposite directions. So L equivalent equal to coming L1 plus L2 minus 2M. Okay. So remember this. Now for mutually coupled inductors in parallel, similar some formula I will say you here. Okay. So remember, when current in the same direction plus 2M, current in the opposite direction is minus 2. If K equal to 0 telling or magnetically isolated, that time this M term will not come, M will become 0. Okay. Now here number 1, if I will take here parallel, and currents are going in the same direction. Two inductors are in parallel, L1 and L2. Then right here, currents in coils are in same direction. If current in the coil are same directions, then what will happen here? Now L equivalent I'll write as L1 into L2 minus mutual inductance will be there between the coil, that is M square. Then L1 plus L2 minus 2M. So this one you have to remember, if current are in the same direction. That means two magnetic fields are supporting each other. Now number 2, similar case parallel. Okay. But what consideration will take here? Now I'll take here current are in the same direction, I1, I2. You can tell like that, I1, I2 same direction. But here one current is this way, other current is opposite. So in this way, what is happening? Now currents are in the opposite direction. Or magnetic field of both are opposing each other. Then what will happen? Now here L equivalent if you want to find, it is L1 into L2 minus M square divided by L1 plus M2 plus 2M. Okay. So this one idea you have to remember. Okay. So this is the mutually coupled inductors in series and mutually coupled inductors in parallel. So this is the series connection. See here, series connection, like this connection series, left right. Here both the points are connected to one common point, and here both the ends are connected to another common point. So that is your parallel connection. Okay. So this is a formula based you remember. So derivation will not discuss here. Okay, the derivation only, that K and L1, L2 you remember. Okay. Now next thing is very small thing, small part is there, that is AC generator. Okay. So little I'll discuss, and during alternating current also we'll discuss more about that little. But now we'll understand how the EMF is inducing, periodic EMF is inducing in the AC generator. Okay. So those who are writing, please pause and you write. I'll go to the next thing. Okay. For the video and write, I'll go to the next thing. Let me complete today this lecture. Okay. Now before that, before AC generator, just a small part is there. What is that small part? A small part is, consider two general cases of the currents flowing in a simultaneously two nearby coils. Okay, so here two nearby coil is there means what is the EMF? So that EMF will discuss little. So two nearby coil is there. Okay, two nearby coil is there. One is L1 and another is L2. One is L1, L2. Okay, C1, C2 we can take what? C1, C2 you can take as a coil 1, coil 2. Now see here what they are telling. Now here total flux in this coil 1, this is the coil 1 suppose, this is the coil 2 suppose. In the coil 1 what is the total flux? That is N1 phi 1. That is what, how it is happening total flux actually. Now total flux is nothing but flux changes due to this coil, that is M11 I1, plus flux changes due to I2. Okay, so that means understand the total flux in the coil 1. It is one general case, it is not under any topic, you just remember it generally by discussing. Okay, now what I am telling here, here in coil 1 whatever the total flux, it depends on the current I1 and also depends on the current I2. So whatever I1 dependent, that is called basically self inductance. This M11 is nothing but self inductance. So they are telling actually it represent inductance due to same coil, and M12 is what? Inductance due to other coil. Okay, now if once finding this total flux, now you know how to find EMF. So EMF is nothing but what it is. So let me write here, this EMF is nothing but minus d phi total flux. So total flux here you can write this one as N1 phi 1 by dt. Now from here I can write now E1 equal to, so I substitute these values, it will come like this. Okay, and now this M11, this M11 you change as L1, M11 changes L1. Okay, so here what you written M11 is nothing but L1. Now your EMF is coming this one. So whatever induced EMF in this, that is E1, whatever they represented basically, representation is given E1 in a induced coil in induced EMF in coil 1. That is how it depends. Now minus L1 di1 by dt minus M12 di2 by dt. Okay, so this expression just to remember. Okay, one star mark give and write. If two coils in general it is there, then what independently some terms are existing. Now one is self inductance, one is mutual inductance term. So both the terms are there. So that is what we want to understand here. Okay. So in general together you coupled things you took together. Okay. Because for certain cases now only just we are finding EMF equal to L1 di or d by dt. So that time when one coil is there, but when both the coil is there, then self inductance also will be there. It will not go no, because in this something happening changes means self inductance also there. So self inductance also there, mutual inductance also there, as two coils are there. Okay. If suppose I am removing everything only one coil, then this term only will come. This will not come. If two coils are there, then this also will come, this also will come. Okay, both will come. Okay, so this is the EMF in the coil 1, that is how much? E1. So E1 is the induced EMF in coil 1. Okay. So please note it down, then I'll discuss SC generator. Okay. So just another 5 minutes we'll discuss and we'll complete this. Okay. I hope little idea you are getting. So please note it down. Otherwise pause the video and note it down. Okay, let me go for the next thing. Okay. SC generator. Here what basically? Now how the alternating current, whatever supply you have in your household supply or in industry supply or whatever supply we are getting now, electricity, that is basically like this type of things arrangement actually. From here only we are getting. So whatever power supply you have in your home, that is basically alternating current. Okay, alternating current or alternating voltage. So how this alternating current or EMF or alternating voltage is producing? That one based on this only, mutual inductance. Okay. That induction, basically induction method. That mutually you can tell it is induction method actually, electromagnetic induction things. Okay, that is basically periodic EMF. We'll get basically periodic EMF. Okay. So now see here what is happening. Now this name is AC generator. AC means alternating current. Okay. So remember here it is alternating current. Okay. So this is the basically what application of electromagnetic induction. So how induced EMF is producing, similar way induced EMF produce here some induced EMF, and that is in periodic nature. Periodic nature means what? That is not a constant value. That is sine, cos, like that it will come. Okay, so it changes its value periodically. Okay, positive, negative, like that. So the main construct, this is generator. Generator means what? It is generating. It is a device actually. Okay. So what this device? This device basically generates alternating EMF or alternating current. That's the main idea of this generator. So one north pole, one south pole is there. So here see, so definitely magnetic field will be from north to south. So like this magnetic field will be there. In that magnetic field like this, in that magnetic field one coil is present. One coil is there here. So you can check here. So this is a coil, rectangular coil is there. Now this rectangular coil will rotate in the magnetic field. It will rotate in the magnetic field. So sometimes it will become like this vertical, sometimes horizontal, sometimes certain angles. So if it will rotate like that, then what will happen? Definitely flux changes will happen. Due to flux change, induced EMF will produce in this circuit. So that is the main idea of this AC generator. So that induced EMF will be in periodic in nature. That's why it's telling alternating. Okay, alternating EMF. Okay, so it is application of your induced EMF or electromagnetic induction. Okay, so now see here. So you can do this picture, do the picture correctly, and you can write AC generator is nothing but it is alternating current generator. Okay, it is a device basically used to generate alternating current or voltage. Okay. Now here some components are also given. Some coil is there. One is this coil, rectangular coil is like this, and one slip rings, carbon brushes. Here axle is there. The axis will be there, and north south magnets are there. Okay, that everything you write. The next come to construction, working. These two things basically we'll see. What is the construction? It consists of a coil mounted on a rotor. Axis of rotation of coil is perpendicular to the direction of magnetic field. Okay. So what is happening now here? One rotor is there. In that one coil is attached and it is rotating. That's it. This is the idea you can remember. Now the coil that is called armature is mechanically rotated in the uniform magnetic field by some external means. That means what? Now this coil is rotating, right? Rotate. Suppose my hand is rotating. I am rotating. That's why it is rotating. So this coil automatically it will not rotate. You have to rotate that. How to rotate? By any like what you know. You can some turbine and all you can connect. You can rotate like that, like how hydropower is coming. Okay. Otherwise, any other mechanical means you have to rotate. Okay. Suppose one turbine is there, on the turbine water is falling, then turbine will rotate. If turbine is connected to this, then this will also rotate. That axle is connected to turbine means this will rotate. Okay. So like that or any external means you rotate. If you rotate, then what will happen? Flux changes will happen. Flux changes will happen in that circuit. Then induced EMF will produce. And the ends of the coil are connected to the external circuit by means of slip rings and brushes. So why these are connected? Now to keep the contact continuously. Okay, because it's rotating, no. Suppose if anything is attached here, if you rotate this one, then it will rotate, it will break. So not to break, the slip rings are there. So it can rotate. So that what will happen? Always contact should be connected. That circuit should be closed. So that is the main idea. Now what is the working here? So construction 3 points you can write. Now working is the rotation of the coil causes the magnetic flux through it to change. So an EMF is induced in the coil. That means if this coil is rotating, so flux changes will happen definitely because it will cause the magnetic field. Okay. Sometimes parallel to the field, sometimes perpendicular to the field, sometimes at an angle I told. So induced EMF will produce in this coil. So in this coil, induced EMF will produce. Now when the coil is rotated with a constant angular speed, the angle theta between the magnetic field and magnetic field vector, so which is north to south, and area vector, that is coil area vector at any instant is theta equal to omega t. Okay. So theta equal to omega t, that normal angular quantities, remember, angular displacement equal to angular velocity into time. Theta equal to omega t, you are writing. Okay. So now here we will obtain this expression. Okay. So you note it down. Note it down. I'll go to the next page. You can pause and you can note. Now the flux at any point or any time t is what basically? Now flux equal to BA cos theta. This one already you know because magnetic flux is what basically? Now magnetic flux is B dot A or basically you can write BA cos theta, and theta is angle between B and A. Okay, so magnetic field and area vector. Now in this situation, if you will see, where is the area vector? And area vector is like this, perpendicular like this, area vector. When it will rotate, this area vector also will rotate. And magnetic field is a constant direction. But area vector will rotate means what will happen? Definitely there will be angle between what? Area vector and magnetic field. Area vector and magnetic field. So that angle they are told as omega t. So now this theta, what I will do? Now this theta is nothing but this theta equal to omega t. I substituted here. So what I wrote here? Theta equal to omega t. That's why my magnetic flux is this one. Now according to Faraday's law, what is the induced EMF? And here the coil turns, n number of turns I am taking. Suppose that coil is having n number of turns, then EMF equal to minus n d phi by dt. This formula already you know. And phi b is nothing but that is magnetic flux already calculated here. So you can put substitute here, already calculated there. So phi b is nothing but what it is. It is here basically BA cos omega t, cos omega t. So that one I substituted here. Now here NBA is constant, it will come out. NBA is constant, it will come out. Now here cos omega t only will be there inside derivative, d by dt of cos omega t. And derivative of cos omega t, remember, derivative of cos omega t is nothing but, that is how much? Now that will be minus, let me write, minus omega sin omega t, minus omega sin omega t. Okay. So already one minus is there here. So this minus is coming. Minus minus will become plus. It will become NBA omega into sin omega t. NBA omega sin omega t. And here you consider this NBA omega. NBA omega is what basically? Okay. E naught. So that is what you write here. This E naught is nothing but, this E naught is NBA omega, which is maximum value of EMF. Okay. Within 3 lines, you got your alternating voltage. Okay. So from the Faraday's law, you know what is your induced EMF. So here when a coil is rotating, then how the induced EMF is producing? Just a flux changes is happening. That flux change formula you wrote. Cos omega t derivative became minus omega sin omega t. Then here NBA was there and another omega came. This total term became E naught, and minus, that minus became plus. Here one minus will come now after derivative, plus, so sin omega t is coming. Now see here, induced EMF depends on the time. Check here, induced EMF depends on what? Time. Induced EMF is depending on the time. Okay, so you can keep everything in bracket, this always. This one you can keep in this bracket so that you can understand omega t there. And this sin means sinusoidal function. Okay, sinusoidal function, it will be what? But if you do here E and T graph, so what will happen? It will be like this. It will be like this sinusoidal graph. So it is changing its direction periodically. Like this one we'll see basically. Now here suppose this coil is having resistance R. Therefore writings, what is your induced current? Induced current. So induced current will be I, which is EMF by R, and it is nothing but E naught by R sin omega t, and here E naught by R is nothing but it is I naught sin omega t. Now this is my alternating current. Okay, so where you can write here, where I naught is E naught by R, or you can write NBA omega by R. NBA omega by R. This is called maximum value of current. Because sin omega t maximum is 1. Alternating current. And what is you are getting? Now here you are getting R. So R is nothing but what it is? Resistance of the coil. So resistance of coil. So how we get induced EMF, induced current? Similarly also we got here, but this induced EMF, induced current is different than whatever we got before. We are getting some constant values, but now it depends on the time. Depends on what? Periodically depends on the time. Okay. So now this is basically called here alternating current or voltage. In the next chapter, alternating current, we'll see about them. perfectly. We'll see what is E naught, Electromagnetic graph, and how the other things are there. We'll see that one. Okay. So I hope you understand here. So pause your video and write down very simple thing I have told here. Okay. And once read and revise. Next class we'll do some questions based on this. Okay. So if you want to write the note, please pause and write. I'll stop the class here. Thanks for watching. Like and subscribe Vidhyalakshmi NEET Academy YouTube channel. All the very best. Thank you.